Hi, it's been a while since my previous ElectroBOOM 101 video, which was about resistors, right? But there's no point to go any further without knowing what a circuit is. What is a circuit? Well, you always need a power supply, like the AC source, and a load. Let me make some room. I just need to clean in front of the camera. Like a microwave oven, for example. I can put in there like a plastic fan. I guess it's not gonna heat up because it's plastic. Now if I turn it on, it draws power from the supply to heat up the How does it work? If there is metal in something, don't put it in the microwave. Just burn my #1 fan. And don't just throw fire on your pile of junk. Ah! We can use a lamp, for example, as the load. You know, a lot of smart people do a very decent job of teaching their knowledge and skills at Skillshare, the sponsor of this video, the online learning community, thousands of classes, and none of them is likely to set their home on fire. You can surely find what you like or need to learn from the list of many categories for free. For the first 2 months, that is, if you use my link to sign up, after which the annual subscription is less than $10 a month, which is nothing compared to the value of knowledge. Let's continue on the whiteboard. Simply put, every circuit is made of 2 parts, a power supply which pukes out power and a load that eats up power. The power supply generates electric current by placing voltage across the load. Of course, energy can escape the system in form of light, heat, radiation and such. But the electric charges like electrons must return to the source. And that's why all active circuits are always closed. Always. It is like the flow of water turning a generator. As we rely on the water cycle to return the water back into the hose, the electric charges must also return back to the source, otherwise we will run out of charges to push out and the current stops. So if I supposedly open the circuit but the light continues glowing a bit, it's because the circuit never really opened. If the circuit seems open but your load is still powered, then you must be missing a component in your circuit, which in this case is a stray capacitor made through the excess length of wire, which blocks DC but passes AC through. So you must be careful about why you are drawing a schematic. There are 2 main types of schematic. One is simply to show the components you have in your design and how to connect them. This is typically for manufacturing or troubleshooting purposes. Pretty straightforward. You just draw it to be most readable, and these lines show how your components connect by conductors like wire. But another type of schematic is what you draw to analyze a circuit. In such a schematic, the results are as accurate as the models you pick for your circuits and components. So there might be a capacitor parallel to your switch. Your supply would have an output impedance. Your wires would have series resistive and inductive components. Your load might have an antenna component radiating electromagnetic waves. But don't let these intimidate you. As a designer, you need to know that these exist and you will learn when to ignore them, unlike the designers of these LED light bulbs who decided to ignore the line capacitance and let their lamp glow. So, in every schematic there are components and their connections. Components connect together through these connecting lines by their terminals. Components can have 1 terminal like an antenna. 2 terminals is the most common one, like resistors, capacitors, inductors, supply, diode and such. 3 terminals is like transistors. 4 terminals and above are like ICs, like amplifiers, processors and such. The connecting lines properties depend on the type of schematic. Again, if you're using this for manufacturing or troubleshooting, then these lines only show how the components are connected, ignoring the wire resistance or other stray components. But for analyzing a circuit, which is our focus here, these are not regular wires. Nothing about them is regular. They are magic wires. Even superconductors don't come close to what these wires are. These are ideal connections connecting point A to point B with absolutely 0 ohm between them. It doesn't matter how long the wire is or how many locations it connects to. The line itself does not affect your circuit. These ideal connections have no stray inductance no matter how long the wires are, and there is no stray capacitance between the lines no matter how close you draw them on paper. These are super wires. Nobody calls them that though. It is important to know that these are ideal connections, and you must realize that in real life you will use actual wires that will have stray components, like I mentioned, that will affect the behavior of the circuit. But don't worry, the engineering design involves a whole bunch of approximations and assumptions. So for most purposes, such a connection is a pretty good approximation of a wire. But if the stray component of a wire becomes too significant, you can show it in your schematic model to make the behavior better to understand and your calculations more accurate. For example, in one of my videos, I made a shunt resistor using this very thick, low resistance wire. Although for most purposes, this thick ass wire is a 0 ohm, for my purpose, I use it as a sense resistor and so must show it as a resistor. Now, when a line connects to another line, it creates a node. A node is a location where 2 or more branches connect to each other. And like those magical connections, the nodes have no effect on your circuit beside connecting the branches. So if you connect components like this, all these connections are no different than a single node. Because since these are connected with magic lines, the line length and the number of nodes don't matter. So you are free to draw your schematic to make it look pretty. Okay, I hope I'm not going too fast. Let's do some intermission. Okay, enough intermission. Okay, let's repeat. In a circuit, there are components that via their terminals connect to each other using magic wires. 2 or more connections from different branches can join in a node. Now let's talk about series and parallel. These two are the simplest connections in a circuit that can help simplify our calculations. Let's assume you have a component like a resistor or a capacitor or a complex circuit like a computer that you can contain all its circuit in a black box with only 2 terminals going in and out of it. If you have 2 of such components connected together by 1 terminal each, then these 2 are in series. If both their terminals are connected like this, then they are in parallel. If there are only 2 components in a circuit like this, then they are both in series and parallel, like a supply and a lamp. Let's do some examples. These 4 components are in series. If I connect another component between these 2 nodes, then these 2 and these 2 are not in series anymore. But these 2 are still in series, and this is in parallel with this branch, and these 3 are still in series. Or here, these 2 components are in series, and those 2 components are in series, and this whole branch is in parallel with the other branch. But if I add a component between these 2 nodes, then nothing here is either in series or parallel. But the whole thing is still in parallel with the rest of the circuit. Now there are important properties to series and parallel connections that you must never forget. Never! Are you ready? When components are in series, the electric current through all of them is exactly the same because electric charges are not leaking anywhere. So if the current enters the branch, it must go through it unchanged. You know what this means? We can switch the location of the components in a series branch and it doesn't affect the circuit because the current through all of them is equal. In parallel circuits, the voltages across all components are exactly the same because otherwise there would be a voltage difference across a 0 ohm magic wire which would result in infinite current, which is impossible. And you know what that means? In parallel circuits, you can switch the location of the components and it doesn't make any difference because the voltage across them remains the same. Like at home, if you switch the location of your TV and your lamp, it doesn't make any difference. This reminds me of the disagreement I had with Professor Lewin in my other video where he was claiming that the voltages across 2 parallel components can be different in the presence of changing magnetic fields. The summary was that our definitions were different and my definition was better, of course. In any case, the properties of series and parallel circuits never break. If you measure two different currents between series components, it must mean that the current is leaking out of the branch through some hidden component, and these two are not actually in series. Or if you measure two different voltages across parallel components, it means that they are not in parallel and there must be a hidden component between them you didn't account for. This should be enough for one video. If you like this type of video where someone like me shares their skills, then you will love Skillshare. 2 months of free premium subscription, mate. Just use my link in the description and sign up. And there you'll find a vast community of people teaching what they know professionally, like lessons on Arduino I'm still going through, or from other categories like animation or film that can help my work. I still need to learn some Adobe Premiere film editing. Learning for free hasn't killed anybody, so sign up for free for the 2-month free trial and get the unlimited access, and I'm sure you'll be hooked.
This course utilizes a practical approach to electronics engineering.
So, have fun.